Lesson 4.5, Dilations. Essential question, can you identify and perform dilations? Can you solve problems involving scale factors and dilations? Let's take a look at the core concept, a dilation. A dilation is a transformation. This is our first one that is not rigid. There's going to be enlargement or reduction. It has a center of dilation and it has a scale factor which tells you how big or how small to make it. Now let's go ahead and take a look at this in a minute after we've looked at this GeoGebra demonstration. Here is the center of dilation, and you can see that when I move the original triangle, that things change on the image too. So depending on how I'm moving, this changes. Now I'm going to do a scale factor of 2. And let's talk about what a scale factor of 2 is. Scale factor of 2 means that the distance from the center to the new location is twice as long as from the center to the pre-image. Center to the image is twice as far as center to the pre-image. Now what's interesting is when these triangles are compared, the angles from the pre-image to the image remain the same. But take a look at the lengths. The length of this side, AB, compared to A prime, B prime. Notice it's twice as much. So the scale factor really affects the lengths of the sides and how they correspond. Let me go ahead and change this a bit here. Okay, now what I'd like to do is change the scale factor to 1/2. Now watch as the triangle is being brought in through these lines here, and I'm going to go to 0.5. Not quite there. All right, so now the new distance from the center to the image is going to be half as much as from the center to the pre-image. So now the scale factor is a little different, and the original length of the side and the new length of the side, that's half as much as that. So the scale factor is not only affecting the distance from the center of dilation, but it's affecting the sides. Again, not affecting the angles. Let's go back to the slide here and let's look at it more closely. So when we have the center of dilation, we have the new distance right here. This is the new distance divided by the old distance. Now this scale factor would also be the same for CQ prime to CQ and CR prime to CR. Now what happens if the point is on the center of dilation? So let's go back to here, and I'm going to make, let's go back to 2. I'm going to take the original B and I'm going to make it right here at my center of dilation. And you can see when a point is on the center of dilation, it doesn't move. It just stays right there. Okay, let's take a look at the mathematics that's going on here on a dilation. The mathematics is happening, these lengths are moving, but what's happening is these sides of the figures are parallel to each other. So we have this parallel property happening for all of when you compare all the sides. When k is greater than 1, it's an enlargement. When k is between 0 and 1, it's a reduction. Let's take a look at this. So we'd like to find the scale factor, which is k, and that is the new distance divided by the old distance. The new distance is here, c to p prime, which is 12. The old distance is c to p, which is 8, and that reduces to 3/2. 3/2 is greater than 1, so this is an enlargement. And we can see that the safety pin is bigger. For this particular problem, k is the new divided by the old, and our new distance is 18 because it's going to c to p prime, and then our old distance to the pre-image is 30. This reduces to 3/5. 3/5 between 0 and 1, and that is a reduction. And you can see the paper clip is much smaller than the original. Let's do it again, and we're going to do k, and k is the new divided by the old. And so here's my new number, which is 3, the new length, and CP is the old 12, and this is 1/4. And we can see that this triangle is smaller than the original triangle. Okay, what's the coordinate rule for dilations? Well, here it is right here. Here's the coordinate rule. It's a lot different than the rigid motion rules. Notice this is the first time we're getting to multiply. In the past, we haven't been multiplying. All right, so let me demonstrate how we go about doing a dilation with a scale factor of 2. So we're going to say 2x and 2y. This is the rule. A prime will now be multiplied by 2, 4 comma 2. B prime will be multiplied by 2, 8 comma 2. C prime will be 8 comma negative 2. Let's go ahead and graph it. 4, 2, which is right here. 8, 2, which is here. And 8, negative 2, which is here. And let's go ahead and draw it. You can see this looks like it's twice as big. This is A prime, B prime, and C prime. And also I'd like to show you that the center of dilation is the origin. And so you can see A moving to A prime, you can see B moving to B prime, and you can see C moving to C prime. Okay, your turn. Stop the screencast and see if you can find the images and then go ahead and graph them. And here's the answer. I wrote out the rule and I went ahead and found the different points and I graphed them, and you can see that the image, it looks like it's 1/3 as big as the original. Now let's take a look at multiplying by a factor that's negative. What happens when you multiply with a factor that's negative? So the rule changes, negative 4x and negative 4y. So this will be P prime, this will be 8 comma 4. Q prime will be 4 comma 0, and R prime will be 0 comma 4. Let's go ahead and graph that. 8, 4, 1, 2, 3, 4, 4, 0, and 0, 4. Now the 4 is showing us that it is 4 times as big. This was the point P prime. This is the point Q prime, and this is the point R prime. So two things are really happening here. We're getting an enlargement, and because we're multiplying by a negative, we're getting this idea of a rotation. I want to remind you that when we have x comma y mapping on to opposite of x, opposite of y, that's a 180-degree rotation. And that is what appears to be happening, that this rotated 180 degrees, plus it got an enlargement. Okay, your turn. Go ahead and try the problem and then resume the screencast. And here's the answer. Notice that it is a reduction, and notice again it is a rotation here. Let's get this cleaned up here. There we go. Okay, let's take a look at applying this in a real life situation. We have a photo. This is going to be our pre-image, and then our image is going to be a sticker. So let's go ahead and figure out the scale factor. That's going to be the new divided by the old. Now remember, the scale factor can be found not only by the distances away from the center of dilation, but using the sides, because the sides also do the same thing as that distance. So the original side was 4, and the new side is 1.1, like here. So this is the new length, this is the old length. And this is kind of an awkward way to show a ratio. So what I think I'm going to do is I'm going to times the top by 10, and I'm going to times the bottom by 10 to get rid of that decimal. And this is 11/40, which is a much better scale factor. Now that is a reduction because it's less than 1, and we can see the sticker is smaller. All right, your turn. Go ahead and see if you can find the scale factor for this dilation. And here's the answer. New divided by old, we're taking the numbers that they gave us from the new divided by the old. That's an awkward way to write the ratio, so I times by 2, and I got 16/9. Okay, last slide. How are dilations alike, different from rigid motion transformations? So here's a bunch of transformations, and let's see if you can identify this one. This one I hope you recognize as a reflection. And this one is rigid. I hope you recognize this. This is a dilation. This is our lesson today, and this is non-rigid. So it's going to become twice as much. I hope you recognize this as a translation, and a translation is rigid. I hope you recognize this. This is a rotation, and this is rigid. Now this one, what's unusual about it is we're not multiplying the x and y by the same thing. So this is not a reflection, dilation, translation, rotation, so neither. And it's also non-rigid. And this is the end of the screencast.